my name is Loïc Fernau. I've been a working student at NXP for almost 5 years now, and in the last 2.5 years, I have been working on auto-wideband and mobile robotics. Currently, I'm writing my bachelor thesis about auto-wideband Follow Me, and that I will show later. I have some stuff already here. But first, why do I want to talk about auto-wideband? You might have heard about auto-wideband already. It's currently being deployed in lots of phones, like the Apple phone, in Samsung phones. Huawei is doing some stuff into auto-wideband. The Apple Nearby Interaction works via the auto-wideband chip from Apple with the U1 chip. You probably have heard of the AirTags and tracking you can do with that stuff. But auto-wideband is also being introduced to cars, doors, and gates, and similar things. In my opinion, auto-wideband has a very good case to be used for mobile robotics and drones because of its features. With our chips, we can range accurately between auto-wideband devices at plus minus 10 centimeter in distance, and we can also measure the angle of arrival of incoming signals up to an accuracy of plus minus 3 degrees. All the while, the auto-wideband is very robust in multipass environments and has a good range of at least 40 to up to 100 meters. And a big feature that's often overlooked is security. Auto-wideband possesses very good cryptographic security and encryption. And also the update rate of auto-wideband is very good. We can achieve ranging rates of more than 40 hertz, and more is definitely possible. Okay, but what is auto-wideband? Auto-wideband stands for every wireless technology with a bandwidth of larger than 500 megahertz. When I talk about auto-wideband, I mean auto-wideband impulse radio that is located at 6.4 to 8 gigahertz and uses a bandwidth of 500 megahertz. This can be done by using a very short signal, a very short pulse duration, and a very low spectral density, so as to not interfere with other communication technologies. This is also what makes auto-wideband great. If you look at the top graphic, there you see the depiction of the time domain of the auto-wideband signal. As you can see, the pulse duration is just about 4 nanoseconds. It's very, very short, but the bandwidth of the signal, the lower graph, is depicted. There's depicted the frequency domain of the auto-wideband signal is a lot bigger. It's 500 megahertz wide. This makes auto-wideband very accurate by enabling it to have a very accurate time frame of when a signal is received and when the signal is transmitted. So you can very accurately measure the time of flight of a given auto-wideband signal. And it also helps a lot in multipass environments. So environments with lots of obstacles and other hindrances in the area, because in the normal line of sight condition, the signal that is received first should always be the direct path signal. And this signal should also always be the signal with the highest amplitude. If that is not the case, then we might be in a non-line of sight condition, because the signal that doesn't come first, like the second or third signal, that has the highest amplitude. So there must be something blocking the way of the direct line of sight signal. And by differentiating this between line of sight and non-line of sight signals, auto-wideband is able to be used in in multipath environments. Okay. We know that the auto wipe is very accurate for the time of flight, but how can we use this for positioning? Well, there are a few ways of doing it. First is just using the time of flight and multiplying that with the speed of light. So what you would do is you just have one initiator and a receiver, and you would range between both devices, and then you can subtract the timestamps from another, and you get the time of flight from the system, and then this would be multiplied by the speed of light, and then you have the distance between both devices. There's a small problem that this is not that accurate. We achieve about accuracies of about 20 centimeters plus minus because of clock inaccuracies on both sides. To improve on this, we do what we call double-sided two-way ranging, where we just send another ranging round. So we range one time from the initiator to the responder, back, and then again back to the responder. And this way, we can subtract the clock inaccuracies of one device, of the initiator or the responder, and reduce the distance error very, very, very well. With this technique, we can achieve distance information accuracies of 5 to 10 centimeters. Another way ultra-wideband can be used for positioning is by using time difference of arrival. This is very different from the use case that I mentioned earlier, by having multiple anchors that are in a defined grid at defined locations, and then have one initiator, like this one, which sends out blink packages at predefined timeframes. So the anchors that are installed in a room, for example, would then all receive this blink package sent out from the initiator. And by measuring the time delay between the reception on each anchor device in the room, you can calculate the position of the initiator inside the room. Also, what I want to show you is another technique that can always be added to every ranging technique I mentioned before, is the angle of arrival. For this, we measure the angle of an arriving ultra-wideband system via multiple antennas. This can be as accurate as plus minus 3 degrees, and is a very good addition to most ranging gear cases. It's based on phase difference of arrival. So we measure the phase difference of two antenna of a signal that is received by two antennas. Okay, but what's the point? In the end, what we can do with our ultra-wideband system, with the angle of arrival plus the distance measurement, we can very accurately measure relative position. It's with a distance information of plus minus 10 centimeters and an angle information of plus minus 3 centimeters. This can be used then for precision navigation, for stuff like follow me work use cases, for convoying, or other things that are done indoors, outdoors, without GPS and with GPS. I will show you some follow me later. But there are also use cases for identification, where you have a pilot or someone else going to a drone, and via the secure ultra-wideband connection, the pilot can identify himself to the drone or something similar. Asset tracking would be an interesting use case, but also last meter delivery, where the rover connects to a customer. For a rover that is carrying some payload connects to a customer, and then based upon the ultra-wideband system, will then securely know the position of the user and move to him. Okay, now I want to show you some of my work on ultra wideband. The first thing I did was the precision landing demo, where we fully autonomously landed a drone on a moving and a non-moving target. As you can see in this picture, you can see the rover is equipped with 4 ultra-wideband devices, and we have a drone equipped with 1 ultra-wideband device. And using multilateration and double-sided two-way ranging, we measure the position and then calculate it with multilateration. And this enables us to land the drone on the rover. I hope the video starts now automatically. Yep, that should, yeah. This is fully autonomous flight, outside of course, but it could also be done indoors, where the drone lands on the rover. This is the first thing I've worked on ultra-wideband for mobile robotics. And the next thing is part of my bachelor thesis. It's about ultra-wideband Follow Me, where I equipped a rover with ultra-wideband and enabled it to follow me. So what we have here is an ultra-wideband device like this one, and the rover equipped with ultra-wideband. I will show you it in a second. You can also see it in the picture, of course. And the rover is measuring the distance and angle information that is coming from the ultra-wideband ranging part, and then uses the very rudimentary body control to publish actuator controls on the rover, so that it can enable indoor follow me. This is part of my thesis, and that's why I did some accuracy tests using this system. And what I arrived to was that the accuracy is way better than expected. We have a standard deviation of the ultra-wideband signal of less than 5 centimeters plus minus, which is way better than expected. You can see on this picture, on the graph, there is the green line. That is the marked track. I laid it on the ground and marked it with tape, and the blue dots, those are the ultra-wideband measurements. And as you can see, those measurements correlate very good with the green marked line. And also, there's a slight deviation at the top of the graph. This correlates with some uneven ground I tested on. I guess it is because the uneven ground moved the initiator a little bit, and then moved the positions a little bit. It's probably caused by this. I also want to show you a video about this. This video was made at the Embedded World Show that happened this week in Nuremberg. And as you can see, there's also, again, a look at our rover equipped with ultra-wideband. And now you should see the rover drive. My colleague Gerald is equipped with ultra-wideband. He has this ultra-wideband initiator clipped to his pants, and also you can also see the remote control for the rover in his hands, but he is not using the controls. The rover is just following via the ultra-wideband system. And as you can see, even with very rudimentary body control system I made in a day, and just using the distance and angle information from ultra-wideband, the rover is able to follow very, very accurately. Okay, how to get started? We have a strong partner network of module partners who supply the ultra-wideband modules like Amotech, Murata, and Sunway. And we also have some in-house design partners like Mobile Knowledge, who are building a development kit that you can buy to enable various ultra-wideband use cases. Included in the kit are some demo use cases, and enough hardware to get a feel for it. Mobile Knowledge also offers engineering support and other stuff, and they're a great help. Yeah. I want to show you one very nice thing. This the new NXP Trimension SR150 using 3D angle of arrival. This is what I used on the rover, because this board can do very accurate angle of arrival in more than 2 dimensions, in 3 dimensions, and the rover you just saw was fully made with this, and the angle of arrival accuracy is way better than expected. Yep. I also want to show you the smartphone integration, because I think it's a very important thing that mobile robotics is able to interact with smartphones. And with auto wideband, this is made possible. Even Apple already is supplying their API, the NIWA interaction kit, for free. And also Android Jetpack auto wideband libraries were released just this month, which are a first step at getting access to the auto wideband capabilities on Android phones. The Apple kit and the Android auto wideband library should all be capable of working with the auto wideband chips from us and from Mobile Knowledge. I would also like to shortly take a look at FIRA, because FIRA is the governing body of auto wideband standards, which enable a lot of the use cases and also do a very much standardization. Yep, and this is an overview of NXP auto wideband hardware. If you want to know more, you can visit nxp.com/Trimension, where there's way more information than in this short presentation fits. Yep. Thank you for your attention, and können wir noch das Video machen vom Rover? Yep, and I want to show you the rover now. I hope he just wakes up. Oh, perfect. So as you can see, the rover is following my hand with the auto wideband initiator. And it can also go backwards, just because of the angle and distance information. Okay, yeah. Thank you for your attention. If you have any questions, go ahead to ask them now. I will try to answer all of them. Yeah, there might not be any questions because most of the summit is virtual. Not virtual, it's face-to-face. So yeah, the only questions I can get are over Zoom, and I don't think too many people are listening over the Zoom. What's the sensor accuracy near metals? Good question. I have not found that that metals per se do a lot of interference. But what is a problem is reflections, and metals do reflect also a lot. So it can be a problem, but it can be controlled. It's not too bad. Yeah, multiple auto wideband modules could be connected together. There's also some work already done on this topic, and it's feasible that multiple auto wideband devices range with each other and do independent orientation. It's a complicated subject, but there's definitely some use case there, yeah, for drone swarms or something like that. The range, range is about 100 meters. We get very reliable range up to 40 meters, and yeah. How can it be controlled if using near metal? I mean, there's a lot of metal around in the studio, like the table here. It wasn't a problem before with metal, and it also wasn't a problem with using the aluminium rods for the precision landing demo. So I don't think it's a big problem. Power consumption, yeah, power consumption is a good question. The auto wideband is very low power. Currently, I'm using just AAA batteries, so this will last a lot of time. But there are also auto wideband tags, like of course the one air tag that can last months. There are some that also from us. We have a SR040 based chip. This is like this big board, and that uses CR what is it, 232 battery, like a little button cell, and this auto wideband is designed to be used as a remote for cars, for example, and there it can last 2 years. Did you do any accuracy on the Z measurements for the system you used on the rover and follow me? Yeah, we did some measurements on Z accuracy on the precision landing. What we have was about what was it? Under 5 centimeters XY accuracy, and Z accuracy was about double that. I guess that is due to the multilateration algorithm. So Z accuracy was about 10 centimeters. Yeah, but we deemed it enough for a drone landing, where if you land, it's not that important to have millimeter accurate accuracy. But yeah, more research needs to be done to that direction. How do you see auto wideband adoption on different, mostly consumer devices on near future? Also, good question. There's we have another demo that's installed there, where we have a auto wideband device mounted to a door for our bike garage, and via auto wideband. On auto wideband on a Apple phone, you can connect to this auto wideband device mounted on the building, and then open the door automatically when you get close to it. Right now, this works only if the iOS app is in the foreground, but there are some in the future. Auto wideband should also be able to work in the background, and there are lots of use cases you can do with smartphones and mobile robotics. I mean, it's in the way it's integrated right now, there you can also already do a lot of stuff. And if it's a seamless experience that works in the background, even better. Okay, I guess that's all of the questions. Thank you for your attention, and have a nice last day. Bye.